Hey, thanks so much for joining us today to discuss overcoming challenges of movement data quality to enable high fidelity use cases. I'm Gabriel Durkin, and I'm a data science director at Foursquare. I manage teams responsible for developing streamlined end-to-end data science processes and tailored ML solutions. We work with our engineering and product partners to refine existing data products and prototype new ones. A little background on me: before joining Foursquare, I made the switch to data science after a career in quantum computing at Oxford and NASA. Okay, for those of you who may not be familiar, Foursquare is the leading location technology platform. We are in the business of understanding movement and places, using technology, one, to understand where things are, and two, how people move through the physical world. Our tech stack helps businesses use location to guide decision-making and unlock revenue opportunities. Today, I'll be discussing key challenges we face in movement data and outline some innovative approaches we employ to tackle those issues. First, I'll give a quick introduction of Foursquare and why quality matters for movement data. Sorry. We'll discuss methodologies for collecting movement data and why using the right technology is critical when it comes to amplifying quality. We'll also touch on the trade-offs between quality and scale and the necessity to build pipelines that are flexible enough to find the sweet spot for different applications. Next, we will talk about driving value in our products by addressing major issues of demographic bias and source panel fluctuations. And we'll end with a high-level breakdown of analytics use cases. And of course, we'll leave plenty of time for questions and answers at the end. But first, let's go into a little bit of background on Foursquare. You may already know Foursquare as an individual app user. We're proud of our consumer app origin, but we've evolved over the past 13 years to become the leading location technology platform. We saw an opportunity for other businesses to benefit from our unique technology, and that's why today we decided to think bigger. Today, we're trusted by some of the biggest names in tech, including Uber, Snap, and Twitter. So about Foursquare's tech stack. At Foursquare, we gain scale by taking movement data from multiple pathways into our core proprietary technology, which then powers all of our data tools and software. We make our data accessible everywhere our customers are in order to derive value for a variety of use cases. In this slide here, we're indicating the parallel ingestion from quite distinct sources. First party is our 1P is our owned and operated apps. Second party is data sourced from our SDK partners. And third party data originates with external trusted data providers. Another takeaway is that there are a diverse array of customers and use cases for this data. I won't go into depth here, but we will come back to at the end of the presentation. Where matters. We know that where matters. The landscape is constantly changing with businesses opening and closing daily, particularly given today's macroeconomic conditions, emerging from a pandemic, dramatic shifts in consumer retail behavior and foot traffic, also potentially a looming recession. The result is unprecedented patterns of human movement, definitely not business as usual. Now, distinguishing a visitor from a passerby is difficult, particularly with signal interference in dense urban cities and busy indoor environments, not to mention nuanced cases like drive-through and buy online, pick up in store scenarios. But when you get location wrong, you risk losing consumers' trust, delivering suboptimal experiences and irrelevant information. That's why the quality of movement data is so important. Now at Foursquare, the value in our data products comes from translating that raw data into meaningful information about places and the movement between. As a result of over 13 years of unique data collection from Foursquare's owned and operated technology on mobile phones, we have created a map of the world not based on coordinates, but rather on actual locations. We collect and leverage an enormous and diversely sourced movement data set. It's actually hundreds of billions of GPS records collected every day. to unlock an unrivaled understanding of the device eye view of the world, accurately capturing movements and visits. And today I'll talk you through some of the innovation we introduced to ensure data quality, things you may not be aware of as an end user, because we aim to ensure you never have to worry about them. So in this context, we'll touch on three aspects of this, three pillars of quality: filtering of noise and synthetic defects in source data, and reconstructing semantically meaningful device journeys source by source. That's one. Secondly, the challenge of harmonizing potentially duplicative and or conflicting data from multiple sources, from first-party apps to third-party providers. And lastly, the need to stabilize and debias outputs in our data products when the upstream sources have their own intrinsic bias and source volumes can fluctuate substantially. Let's move on to sketch out some of the requirements for detecting movement. What technology is being used at Foursquare? First, how do we get movement right in a primitive sense? We rely heavily on GPS data to reconstruct these daily diaries from mobile devices. As I mentioned before, our movement pipelines might absorb 100 billion pings. By pings, I mean coordinates and timestamps for each individual mobile device. That's 100 billion GPS records per calendar day of observation. However, inaccuracy in GPS signals because of urban canyons, weak indoor signals, and other noise sources may indicate that a mobile device user is half a block or more from his or her actual location. And in dense urban environments, this can mean the difference between, let's say, a taco joint and a clothing boutique, or a bank and a shoe store. So how can you solve for this and ensure there is truly a visit taking place and that it's registered as a visit to the right place? Well, first is the temporal element. How do our algorithms differentiate between visitors and someone passing by? And so this animation is showing, for instance, this GPS trail associated with this device. There were actual visits in blue. You can see the venues that are actually visited versus the ones that are just in proximity, which are in this cyan color. As the user passes by, they don't actually visit these places, even if they do spend some time in proximity to them. How do our algorithms differentiate between visitors and someone passing by? We do this using our proprietary multi-sensor technology for movement understanding. This can accurately detect and segment different types of motion and its scale, solving whether the device is at rest or in motion, and is the motion, for instance, pedestrian or vehicular. We use inputs of speed, distance, direction, and dwell time, and even the shape of a person's ping trail to build a semantically meaningful daily diary for the device owner. And beyond that motion primitive, the next layer of understanding comes with asking, okay, so the person stopped here. How to know that they stopped at venue A and not venue B? At Foursquare, we use what we call snap to place. We've built our own proprietary database of points of interest using place shapes, collecting signals from visiting devices to build a picture of a place structurally in terms of movement of devices in and out and around that place. Context clues like time of day and venue popularity provide an additional layer of insight to optimize our model predictions. So those you might think of as features for the ML model. Our real-time feedback system confirms and continuously improves our model accuracy. So we have real users using our apps, and they can help us calibrate these models, because users still will go through the process of manually checking in at venues, which harks back to one of the original applications of Foursquare apps. So another important challenge when it comes to movement data is we need to ensure both quality and scale. Some client applications favor quality or precision, for instance, analytical applications. This I call depth, whereas others, perhaps on the marketing side, are looking for data volume, audience reach, and scale. And this I call breadth. Fortunately, the movement data pipelines we build at Foursquare are flexible and tunable to optimally trade off breadth and depth for each application. So addressing the challenge of quality and scale, how do we get there? At Foursquare, we have a unique competitive advantage enrichment, we gain initial scale by taking movement data from a large variety of different sources. You know, I mentioned already our data pipelines ingest over 100 billion pings of GPS records per day. A process of data fusion and reconciliation from these diverse sources mean that, in effect, the whole is greater than the sum of the parts. We're able to compare the storylines that different sources are telling about the same user, and sometimes one provider can fill in the knowledge gaps present in other sources. In extreme cases, one provider may contradict the location of the user when all other sources agree amongst themselves about that location, and we can use a voting system to reject those conflicting data. A second competitive advantage is provided by our consumer-facing apps, Swarm, City Guides, and Rewards. The unique user feedback that they provide allows us to train and fine-tune our models, providing us with check-in ground truth data. Now, I should say that all users provide opt-in consent, and because we present the utility to our customers in a transparent way for sharing their location, our opt-in rates are higher than industry standards. We then use this first-party data and data from our SDK partners to further enrich, challenge, and harmonize the data from third parties. Now, in the following few slides, I'd like to give some flavor of how our movement engine works. This is not so much about injecting fancy cutting-edge ML algorithms. I find it leads to more effective solutions if we take a step back to frame the problem correctly and architect solutions in the right modular way. And I'll present some of that in the next couple of slides. Bringing all of this diverse data, these hundreds of billions of pings into our pipelines presents many challenges for data quality amplification. To start with, we set up blacklists for both locations and devices that will result in Foursquare not using that data. We also set up filters to remove bots and fraudulent data. So what about what's left? On top of the remaining data, here are some highlights of our process for reconstructing semantically meaningful user journeys. We've built innovative systems for data source deaggregation and eventual reconciliation. It's quite a mouthful, but what I mean is, in terms of architecture, we run parallel independent pipelines for each source, which help handle any panel instability. And then within this architecture, we have provider-specific algorithms that are tuned to unlock provider-specific quality monitoring and noise filtering, and subsequent testing of inter-provider consistency, deduplication, and eventual harmonization into a single fused device timeline for one user. A second aspect of this that I want to highlight is movement can be more confidently identified, say, than stops from raw pings. And this allows more flexible stop definition beyond a simple density or clustering approach would allow. Richer geospatial understanding is made possible as movement and stops are really two sides of the same coin, or yin and yang. You can think of stops as an absence of movement. A third highlight is we are training on our own app feedback. As I mentioned before, we're able to leverage first-party user check-ins to validate our movement and visits algorithms and perform data conflict resolution with third-party data. Another key component in getting to high fidelity data products, we have aggressive and precise noise filters for data quality in the upper funnel, and I'll present some examples of that. And finally, privacy controls are central to any improvements we make in R&D at Foursquare, and this carries on into the development cycle. The data science team works very closely in collaboration with Foursquare product and legal and privacy teams in any new products we build. Okay, let's look at the raw data for a second. So this is obviously Manhattan, parts of New Jersey, part of Long Island. Something is evidently wrong with some of this raw data. Most people in this industry might be familiar with these mysterious ubiquitous crop circles that started appearing in GPS data last year. If we took the same snapshot of pings, this is over a course of a couple of days. If we did this in 2020, you wouldn't see these circles in the data, these filled in disks. So there exist issues that are easy to recognize visually, but a challenge to remove systematically and at scale. Quality amplification begins at the ping level. When we project the classification results on a Foursquare Studio map, this is our visualization tool at Foursquare for geospatial data. the output of the movement understanding pipeline paints a beautifully segmented picture of stops, the green points, moving segments, colored blue, and synthetic noise and defects, in particular those crop circles that we saw previously in red. We are painting this 3-color picture algorithmically. So once identified, this red ping noise is simple to filter out, allowing us to build more confidently on the remaining ping data, the semantically meaningful stories for the users moving through the physical world. Obviously, no real user was moving, like a Roomba in a circular room, just filling in a disk of pings. That is not physical, it's synthetic. Now, we haven't necessarily understood the origins of these synthetic pings in these disks. We actually have a collaboration with New York University master's students working on their data science master's degrees on exactly that. Here you're looking at just 1,000 users in Los Angeles during a particular week of 2022. And this is what I call maps without maps. What I mean is the blue colored movement data itself is tracing out the road and street networks using only the ping sequences and how we've determined movement from those ping sequences without reference to any base map or prior. If I remove the base map here, you would still easily see the road structures because roads are associated with movement, and we're confidently and effectively identifying movement, and that's why the blue pings are able to trace out the roads and street networks in Los Angeles. So let me work through some of the components of what we build for movement. As a simple example of one input to understanding and classifying movement is what we call the vector scalar distance ratio, which is kind of a mouthful, but it's a trail shape metric. Okay, so here are 2 ping trails of 12 pings for a single device or user. So if you think about, on the left, you have a ping trail where a device over time is sort of meandering around and not really moving very far. The ping trail itself is kind of coiled up. And then on the right, this is definitely a trajectory that's moving from A to B. It's less meandering, it's more direct. And one way to capture the difference in these two these two shapes of ping trails is if you think about the total distance traversed, like the sum up all of the distances of the little black arrows that join each of the pings over time, that's what we call a scalar distance. But then the actual overall distance traveled, from one ping to the next over those 12 pings, on the left side, it's this red arrow, and on the right side is this blue arrow. And if you just compare those two distances, the net distance traveled is the vector distance, and then the scalar distance is just the sum of all the path segments. If you just compare those two, the ratio can be at most equal to 1. So it's a nicely restricted metric between 0 and 1. And obviously, when movement is occurring, this ratio is closer to 1 than it is to 0. And so by introducing a threshold on this metric, we can map from the trail shape to a classification of in motion or at rest. This metric is surprisingly robust against noise, yet still effectively identifies different motion types. For instance, a device moving in a car on the highway or an old lady shuffling down the street with her shopping bags will both be identified as moving. If we instead segmented motion types on device speed, we discovered the results turn out to be much less interpretable. So I sometimes think of this as like the spaghetti shape metric. Spaghetti that's coiled up and in the bowl has a low vector scalar distance ratio, and when you pull it up onto your fork, the vector scalar distance ratio increases. So the algorithmic processing of raw data imbues it with geospatial intelligence. This idea of moving up through the data pyramid from raw data to information to knowledge and then wisdom, converting it into actionable information and value to clients. And here I want to give a high-level overview of the sequence of pipeline steps, of which this VSDR, the spaghetti shape metric from the last slide, is just one component. The process of getting to semantically meaningful user journeys is one of hierarchical harmonization from individual pings to stop and moving segments and on to device timeline generation. I spent most of my life as a physicist, so pings and segments I think of as like atoms and molecules, and And so we're just moving up through that kind of hierarchy of complexity. First step is the removal of the noise in synthetic data, for instance, the crop circles that we mentioned. Then follows a ping level classification that tags pings as moving or at rest using inputs such as the spaghetti ship metric, this vector scalar distance ratio metric. Next pings are bracketed into moving and stationary segments with some tolerance for mismatch between ping types and parent segment class. So you can see here this moving segment has some stop pings inside it, but it's predominantly moving pings. Next, the pings within a segment are harmonized or homogenized. So the tags of the outlier pings inside each of those lassoed segments then gets mapped to whatever the majority vote is within the segment, maybe. From the sequence of moving and stop segments, a complete user timeline is created. So you can think of these pings as moving through time from left to right. This is for a particular device and a particular provider. And so from this sequence, a complete user timeline is created throughout the day, if you think of time moving from left to right. And you see the intervals associated with each of those segments. And note, this is for data for a particular source provider. The final stage of harmonization involves the reconciliation of multiple timelines, one created from each third-party source. And in reality, these don't always agree. So there is definitely a challenge here of harmonization and reconciliation. So these multiple timelines undergo a proprietary data fusion process into a single amalgamated timeline for that user or device. Here we only show 2 providers, but typically for any device, there might be 10 or more source timelines to fuse. I like to think of these timelines like DNA sequences. Here we've discussed only 2 segment types, moving or stops intervals. But the next level of complexity means breaking stationary segments into home visits and out of home, perhaps work. You might want to define a work location. For movement, we can segment further into pedestrian and vehicular movement. And the whole goal here is to, build up a more complete understanding of that daily diary of the device owner. So now there are at least 4 components to these temporal DNA sequences. And the goal of making the fused offspring timelines semantically meaningful means answering questions like, where is the owner's home? Did they start and end their day at home? And there are challenges with home designation too, because up to 25% of the population doesn't work 9 to 5 hours. So it's not always as simple as asking, where did this device spend its time overnight between the hours of 11 p.m. and 5 a.m.? And are overnight stays considered a home visit? What if you spend the night at your girlfriend's house? And so it's worth making a distinction between permanent home addresses and overnight stays. There are plenty of challenges as we build out these models for movement. I realize I'm supplying high-level answers to some while raising more issues along the way. I'm not claiming we have all the answers, but that we have a process in place and that Foursquare is actively engaged and continuously developing new and better approaches to cracking this nut. So now that we've given a flavor of how we think about movement and the creation of meaningful device timelines, how do you approach your evaluation of location movement data to assess data quality? How do we calibrate the outputs of these movement and visit pipelines to ensure high fidelity or representativeness to patterns of human movement in the real world? Even with this process I just described to reconstruct these semantically meaningful daily diaries from the raw GPS pings, there remain questions of demographic biases and data volume stabilization. At Foursquare, panel demographic biases are addressed by a normalization scaling called SAG. S is state, the home state. A is age, the explicit or predicted age of the device owner, and gender is again the explicit or predicted gender of the device owner. And we are continually exploring how we can innovate here and improve our models to be even more nuanced. And so what I mean by SAG there is that we cut the device owner by these 3 dimensions to put them into a 3-dimensional demographic bucket. But often demographic details are unknown, in which case we might estimate geographical home locations. Now, devices we snap to the center of the residential parcel that the home falls within, and we make sure to dilate the size of that residential parcel so that it is sufficiently public, and that we're not giving too precise a location of someone's home downstream. This home information then provides a bridge to public census data, so demographic details can be estimated. These inferences are applied at the aggregate level to faithfully represent real population movements in the urban landscape. I want to mention also that given large-scale aggregation and normalization, the derivative products bring anonymity and privacy for the original device users. Aggregation equals anonymity. And as a data scientist, obviously the value comes here in patterns, in seeing a sufficient sample size to reach, statistical significance. And so when you make that a requirement, for a particular pattern of movement to be, considered significant, then, with a certain sample size also comes anonymity for free. So here's a closer look at how normalization works with an example. The state, age, gender score is calculated simply as the number of people who live in a given SAG bucket according to US Census, divided by the number of Foursquare panel users in that same state, age, gender bucket. So let's choose an explicit case. Foursquare has 500 women aged 20 to 24 in the New York State in its panel, and the US Census data shows that 50,000 women aged 20 to 24 actually live in New York. Then each woman in the panel who is in this age range and lives in New York would count as 100 people, because the SAG score would then be 50,000 divided by 500, which is 100. Okay, final slide. In summary, I've touched on 3 pillars of Foursquare's approach to data quality. 1, filtering noise and reconstructing semantically meaningful device storylines. 2, source harmonization, deduplication, and data fusion. And 3, stabilization and debiasing in derivative data products. So to finish, we should talk briefly about applications. In the most general framing, I think there exist 3 layers of increasing sophistication in how our movement and visits products can be used by our clients for analytical applications. Starting with the most basic and commonly encountered, our partners would like to describe accurately the world of their customers, their trends over time, patterns of movement and visitation. So that's like if we're interested in coffee shops, if we use that as an example, I might ask, which coffee shop has the most foot traffic to it in all of California? I think the answer is a coffee shop in Berkeley. The next level of sophistication is prediction. Our clients might want to predict what their customers will do in the future, or predict where business could be located based on the features of the surrounding environment. Now, you might wonder as a client, am I using prediction correctly? For instance, if I'm interested in site suitability, where should I open my next coffee shop? Should I be trying to predict where coffee shops already exist? Because in some sense, that's what prediction is doing. So there's a subtlety here of distinguishing correlation from causation. Perhaps I don't just want a prediction algorithm. For instance, in the coffee shop example, there may be a strong association of foot traffic with coffee shops, but then you have to ask, before there was a coffee shop there in that location, was there a lot of foot traffic? Was it because there was foot traffic already that someone put a coffee shop there? Or is it because someone put a coffee shop there that then that attracted more foot traffic? So this brings me to the final and most sophisticated application, which is, human in the loop decision makers really want to ask and answer what if. That is, they want to leverage our data products and insights to fuel business decisions like, how will my revenue be impacted if I open a new office or coffee shop at this location versus that location? So that's it. I hope you enjoyed my presentation. I think next we have time to take some questions, but first I want to say that really I've only scratched the surface today. As you can imagine, the devil is in the details with this work. And I want to call out the many talented data scientists and engineers at Foursquare who are key to our continuing to find innovative solutions for our clients in this geospatial data space. Thank you.